Record. So in this section, in section 3.3, notice, by the way, this is corresponding to your book, right? 3.3. So I'm not going over 3.1 and 3.2. This is just 3.3. Okay, we're just going to 3.1 and 3.2 was all the trig that I've been teaching you in the last, few days, that kind of stuff. That's really what goes on in 3.1 and 3.2. So we're going to spend today, we're going to spend tomorrow, Friday, Monday, probably like 4 days on this section alone. Okay, there's a lot to do with it. Your next test, when is your next test? Anybody have it actually open? October 21st? Is that right? That sounds really far. I think that's too far. That sounds right?
It's like 1 month, yeah. I think you said
you have it?
June 8th or something?
Oh no, 21st. Okay, you know why? I forgot because there's the 4 days of Kairos that aren't in school, so I counted for that. So your next test, I'll tell you now, will mainly be this section and probably the beginning of chapter 4. Like 4.1 and 4.2 most likely. But it's going to be a lot on projectiles. Okay, there's going to be a lot of work on this. Do I have you guys for a double tomorrow, or is the other class double tomorrow? No double for you guys tomorrow? Okay. So your lab will do on Monday. And we're going to do a lab on the computer with projectiles and moving and looking at the angle and change.
Our double's on day 3.
Day 3. They're day 1. That's what it is. Okay. So we've got 3 objectives. First, we're going to recognize when an object is moving in some sort of parabolic pattern or a projectile. Understand the path. And then the third thing, resolve velocities into components to solve by component-specific equations. Okay, and I'll explain what I mean by that in a moment. Okay? So, a projectile is simply defined as any moving object that can be modeled as a point in space. What I mean by a point in space is this. If a rocket is launched, you're not looking at the whole rocket really, right? You're looking at the rocket and you're saying, okay, well, let's look at the center of the rocket, or what we call the center of mass. And then as a result, we can travel or track the center of mass. So the person's center of their body is what we're looking at here. Maybe like, see where the person's belly button is? That's where you would consider that to be like the point. So this is the person's, center of mass right here. And then when they jump, now they're suddenly a projectile. Okay, because they're moving in 2 directions. They're moving vertically and horizontally. So projectile motion here, when we're looking at this, is 2-dimensional motion. It's also free fall with horizontal velocity. So what I mean is this. If an object is only launched horizontally, it's considered a projectile still, because over time, it will start to fall like this. Imagine you have a cliff, and an object is launched off the cliff like this. It looks like it's only horizontal motion at first, but the path that this will take will be this. So in the end, it will be parabolic, it will be projectile motion, although initially it may seem like it's only horizontal motion. Josh, so the path of a projectile that it follows, we said again, is parabolic. Now, what do you think this is trying to illustrate? What do you think the black versus the blue dashed path is trying to show that we could have? Okay, so if it's a higher angle, maybe it follows that higher path. What else? There's many answers that you could think of here. Okay, the motion that you theoretically, not optimal, but theoretical motion versus what actually happens. That's what I was thinking about, and I'll explain that in a minute. What else do you think of when you see this? Somebody heading the ball, yes. Maybe the position, hit them on the head, right? Hit them on the top versus the front of the head, it will go differently. Now, what I wanted to just go over real quick is that the realistic path would be the black dashed line. But in class, what's that? They're both with gravity, because they're both falling. But the black line includes what kind of resistance? Air resistance, okay? So what we're going to do in physics this year, which you're going to do pretty much in all physics courses until you learn calculus, is we're going to assume that there is no air resistance, or it's negligible. So the path traveled without air resistance is the blue path. Okay, the blue path is without air resistance. The minute air resistance is encountered, it's going to automatically slow down the object. It's going to slow it down so that it would follow that black path right there. Now, if we think about this, realistically in life it's not true. And in life you can have a wind that helps you or a wind that hurts you. If you ever kick a soccer ball before, I use soccer because it's a great example, baseball not as much. But a soccer ball, on a really windy day, as a goalie, you always want to keep your kicks down, because if you kick it higher, there's more wind up in the air as you go higher, and suddenly if the wind is against you, you'll kick it and it'll start coming back. It'll drift backwards. So versus, if you keep it low, it won't get affected by the wind as much. So the wind can act against you, or maybe the wind is behind you. And in that half, as a goalie, you know what, I'm going to put a little bit of air underneath it so the ball will carry further down the field, maybe, depending on what your desired goal is in that problem, or in that play. But remember that air can help or hurt you. We're going to assume that it doesn't do either. Okay, that it is negligible. Whenever I say negligible, I mean it doesn't really affect the problem that much. Okay, it doesn't really have any major impact on the problem. Okay? Alright. Let's take a look at this next thing now. And this is where we get our idea of objects launched horizontally. And I need to do a quick little demonstration, so I'm going to steal your desk, Josh and Jen, if you don't mind. You can leave your calculators just moving for now. I'll do this. This is your science. So keep a flip engine. Just click that up. Alright. Two people want to volunteer to do something? It's very simple. Mike, come on up. Jake, come on up. Sorry, Josh. So that first. Alright, one. Jake. Okay. Now, here's what they're going to do. One of them, it doesn't matter who, because you're over there, you can be this person. So what Mike is going to do is Mike is going to roll the tennis ball off the table. Okay, he's going to take this side and just roll it, and it's going to fall off here. What Jake is going to do is Jake is going to wait right here with this tennis ball. And as soon as that tennis ball leaves the table, he's going to drop his. Okay? And we're going to hope that we see something interesting happen. Back up a second, actually, so we can see all of it. Yeah, so what I want you to do is this. I want you to stand back here. Okay? Hold the ball on the table for now. And imagine if you were just going like this, but keep it at the exact height of the table. So don't move the height, like right there. You see what I'm saying? So hold it down and just slide it over a tiny bit till it's off the table. Okay, now wait there. Is he lined up with the table? Is the bottom of the ball lined up with the table? A little bit higher? Okay, and now move left a tiny bit also. Okay. So, as soon as that ball gets to the position right here where it starts to fall, you need to let go of that.
Yeah.
Make sense?
Yeah.
Okay, so you're gonna roll it up. When you're rolling it, oops, sorry. You don't have to roll like, you don't have to roll really slow. You can roll, don't whip it, but keep it on the table. I don't want it to bounce. So just like a nice, smooth, look fast. Maybe you want to go off this side of the table so we can try to see this. You went a little early. Try it. What do you think I'm trying to get to happen? What do you think should happen? Ball? Yeah, it should reach the ground at the same time theoretically. And if we do it where his timing is right, it'll work. Verti's a little bit faster. Ooh. Did you hear only one bounce there? Isn't that kind of amazing to think about? So Rachel, think about this, right? If I extrapolate this idea, if I take a bow and arrow, right, and I pull back on the bow and arrow and I let go, and then I take a BB gun and shoot them at the exact same height and both horizontally, they both hit the ground at the same time. Cool. I mean, obviously with their resistance things will change, but theoretically speaking, if an object is launched horizontally, another one is dropped, they act the exact same way. The time taken is identical. So we're going to take this idea and we're going to use this in one of our problems in a minute. And that's what this diagram is trying to show you here. So Jake would be the red ball that's falling down. That would be like a free fall. And at the same time, Mike launched his horizontally. And what they noticed, and you could actually buy something to do this. You could have something like a spring-loaded thing and launch it at the exact same time. You let go, and you would see this happen like that. But that was the same idea as what's happening. And every instant in time, notice that these all line up. The ball is at the exact same height every single time a snapshot is taken along the way. Okay, thanks guys. Okay. Very simple, but it's something that we're going to need to know. So we have to utilize that idea. So, keeping that in mind, let's take a look at our first example. Okay, let's go to the next slide and look at the first example there. By the way, it works so much better in this class than the other class. We couldn't get it. It was always like off, like the ball, like boop, 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 boop. There was like a small discrepancy in it. So you guys got it on the second try. That was good. Very good. So let's say we're looking at a bridge, okay, and it's 300 meters above the ground, and we've got Tom Cruise. He's in another movie that he's starring in. Who knows what it is this time? And he's in this sticky situation, meaning he's got to get away from these people that are chasing him. And he's on the bridge, and he decides he's just going to run off the bridge.
Jump.
Not even jump, just run right off. he realized, he's like, I'm really good at physics, I can figure this out. And I see there's like a platform that's floating, and it happens to be a bouncy castle. And he's like, I want to land on that so I don't get hurt. Floating in the river. So he runs off with only horizontal velocity. Okay? So I wrote he jumps off the bridge, but by running off the edge only in the horizontal direction. So like the tennis ball that Mike just rolled across the table. That's Tom Cruise running off the bridge, just running straight off. He hits the water, and after a horizontal displacement of 50 meters, okay, so he's fallen down 300 meters, and he's gone horizontally 50 meters. And we want to figure out what the velocity is with which he jumps or runs off the bridge. I should say runs instead of jumps. Okay, what is the velocity with which he ran off the bridge? With which he ran, I should correct that for next year too. Ran off the bridge. All right? So, what do we know in this problem? What is something that's given? And you have to consider the vertical and horizontal as different things, so specify when you give me answers. Jen, what's one thing you know?
You have VIY, which is 3 hoops. Am I too far ahead? 300 meters?
You have y.
Yeah.
You said VIY, just y. That's all you have right now is y. So you have y, and what is y equal to? It's not 300 meters, be careful. Yeah, it's negative 300 meters. Let's remember the negative. Simply because Tom Cruise is falling down toward the river, not up. Okay, so the displacement vertically is negative 300. Good, that's one piece. And what else do I have?
We know the it's like calling that.
What is it?
Negative 9.81.
I'm going to put AY for acceleration in the y direction. And very good, Victoria. Negative 9.81 meters per second squared. Good, good, good. I know something else. What else? There's another number in the problem. Figure out what it means.
X is 50.
Yep. His horizontal displacement is 50 meters. Okay, let me draw you a quick diagram in case you're confused as to what's happening. So here's the platform. Here's the water. Okay, this is a suspension bridge. Make-believe cables are holding it up. Here's Tom Cruise, modeled as a point in space. He runs off the edge of it, and as a result, ends up falling 300 meters, but ends up going out this way, 50 meters. Trying to make it out the door, sneeze, or not sneezing. All right, so he moves out 50 meters and down 300 meters afterward. That's really all we know right now. There's one other piece of information I want to discuss, but I haven't really gone over yet. Remember what we said about air resistance? We consider it to be, what's the word? Negligible, doesn't really affect the problem. Now, air resistance in these problems would give you some sort of horizontal acceleration. If I'm running, right, and there's a wind that pushes me back, wouldn't that be like a negative acceleration? Or if I'm running down the street and there's a wind behind me, that's like a positive acceleration pushing me. But we're assuming there's no air resistance. So what would the acceleration be in the x direction if there's no air resistance? Yeah, it'd be 0. So here's an amazing thing that we're going to notice this year. Every time we solve a projectile motion problem, we will always use the same formula in the x direction. What formula is the only formula, the only one, that involves no acceleration? There's only one formula that doesn't have acceleration in it, that we've learned so far, obviously. The first one that we did this year didn't have acceleration. What was it? Close, not V over.
Or V is equal to X over T.
Yes, V equals X over T. So we don't know what formulas we're going to use in the Y direction yet, but I definitely know in the X direction, it's going to be something with X over T. 1 second. And let's just call this VIX for now, meaning the velocity in the X direction. Okay, I'm going to pause there, okay, where Tom Cruise jumped off the bridge by running straight off. And he ran for, in a horizontal direction, and he ended up 50 meters out from the bridge, and he had fallen 300 meters down, so we listed those givens, okay? Now, since he ran off the bridge horizontally, and he didn't jump vertically, what would VIY be? Because he's only running horizontally. It'd be 0, good. Because remember yesterday with the tennis ball, where if we drop the tennis ball, or if we roll the other one horizontally, they hit the ground at the same time. So whenever an object is only launched horizontally, it's like a free fall. So VIY is 0. Now, we're trying to find the initial velocity, which is Vix in this case, because he's only running horizontally. That's our goal. But we can't do that. The bottom formula here that's listed that we're always going to use in the x direction, as we mentioned yesterday, we can't find Vix because we don't have time. We've got the displacement x, that's 50 meters, but I don't have the time. So anybody have an idea to how we can maybe find the time if it's useless in the x direction? What can we try and do? This is tough. It's not an easy way to do this. Remember, think back to the tennis balls. If one was rolled horizontally and one was dropped, they took the same time to hit the ground, didn't they? Yeah. So couldn't I just look at the y direction and consider this problem like a free fall and find the time it takes? Because the time it takes to fall 300 meters if I just drop something, instead of Tom Cruise running out this way, is the exact same time. So I can only look in the y direction if I want to and find the time. And then I can take that time and use it in the x direction. The reason this works is we call t what's called a linking variable. It links the two directions together. Maybe I'm running this way and it's all horizontal. But the time it takes to do something doesn't matter whether you're horizontal or vertical. Time is time. It doesn't matter which direction you're looking in. So although we split this problem into two directions to start, when we find the time in either direction, we can use it in either direction. So if I were able to find the time in the y direction, let's just use it in the x direction. So in the y direction, if I'm trying to find the time, how can I go about doing that? What formula might I use that involves time? You have three choices, remember. Three choices. One of them does not have time in it, so that's out of the choices. So you really only have two choices left for that direction.
Isn't it VIT plus 1/2 AT squared?
There it is. Good. Good, good. AT squared. Now, I'm going to put little subscripts in again. Remember, I'm going to put these little subscripts in to indicate them in the y direction. They're not variables. Those little y's that I just drew in right there. This is not a variable. This is not a variable. It's a subscript indicating I'm talking about the velocity in the y direction, the acceleration in the y direction. But what's VIY? What did we say the velocity was in the y direction to start? It's just 0, so this part doesn't really matter. Remember, this just goes to 0. But that arrow to 0 showing it's going to 0. So it turns out that in the y direction, my formula is actually quite simple. Okay, it's 1/2 AT squared. Oof, thank you. It's 1/2 AT squared. So, I can try and determine the time in this problem. Solve for it algebraically. How do you get rid of a 1/2?
Y by 2.
Yup. How do I get rid of the A? How do I get rid of the A? The acceleration. Divide by A. So let's multiply by 2, making this 2y equals a t squared. Then divide by A. Giving me t squared equals 2y over A. Now I take the square root. So it's 2y over A underneath a radical. Why don't I need the plus or minus this time? Can somebody explain that?
Because time can't be negative.
Good. Time can't be negative. Okay? We're looking at time being positive. So take 2 times the negative 300. Divide that by negative 9.81. And take the square root of that to give us the time it takes Tom Cruise to hit the water. Again, 2 times negative 300 over negative 9.81 under the square root. Jake,
61.2.
take the square root. Did you take the square root?
Nope.
So take the per second square root, second answer. So take the square root of the previous answer that way. What do you got, Jake?
7.8.
That's it. 7.8 seconds it takes Tom Cruise to hit the water. Now, this is as if he was just dropped. Remember, now we're looking as if Tom Cruise was just falling as a free fall from that 300-meter distance. But he's not just falling, he's running horizontally like this. So in the time that he's falling, he's also moving this way. Again, it's like if I was an airplane going like this, right? If I let go, when I let go here, it doesn't fall straight down, it falls this way. So Tom Cruise is not really falling straight down, he's moving to the left or right. So it turns out that we could use that time it takes to fall as the same time it would take him on the left-hand side. So take this quantity and use it for t. This is our linking variable, because it links the two equations together. It's the linking variable. You can use it in both directions always. So let's go ahead. X was 50 meters. That's how far Tom Cruise was able to move horizontally after he ran off the bridge. And it took him 7.8 seconds to hit the water. So we can determine the velocity he needed to do that by dividing those two quantities. 50 over 7.8 gives us 6.4 meters per second. So again, if Tom Cruise or if an object had just fallen, that's how long it would have taken. But he was running horizontally. It still takes that long, but in that time, he was able to cover 50 meters outward. Okay, outward.
In every problem, should we solve for y first and then link?
It depends on the problem. Sometimes you'll have enough information in the x direction to find time, and then you might need to use it in the y direction, or vice versa. Okay? It depends on the problem, Jake. So let's look at the next problem to see what I'm talking about here. What's it called? A plane or a bomber, really, that's delivering a package to a remote island. So if I'm a plane, watch my hand, and I'm flying, and I drop a package, it doesn't fall straight down, right? Again, it falls outward like a parabola, as if it's being launched horizontally. And you've seen this before if you think about it, and you should never do this. But if you did ever throw something out the window, like a piece of gum or something when you're in a moving car, it doesn't move like that. It gets pulled back. It starts to move with you, but it curls. It doesn't actually move in a straight line. It's the same thing. If something moving across the air were to just drop something, it moves like that. It doesn't fall straight down, obviously. So in this problem, what we're trying to do is this. We're told that this plane is flying 500 meters above the ground. It has to drop a package. We know the plane travels at 607 kilometers an hour, or 186 meters per second. So we want to know how long it's going to take to hit the ground, and how far away should it be from the island before it drops, right? How far will the package travel horizontally? So this plane needs to know, and this was really important in like World War I and World War II, when they had to drop off med kits and medical packages and food supplies. The plane would need to know, okay, I'm at the right location, drop it now. And the package would fall like this and land in the appropriate landing zone. So we're trying to determine how far is this package going to move horizontally once it's released. It releases and it falls. How far is that so we know how far back the plane needs to know when to drop the package and how long it will take to hit the ground. So it's a very similar problem than the last one. It's almost identical actually, except now we don't know VIX. We don't know the speed Tom Cruise is running at. We're trying to figure out in this case, in this problem, the displacement instead. Give me a second. We have exams, so we have 3 minutes. Can I keep going? Okay. I don't want to make you watch this tonight. I'd rather get through it today. So X is the unknown that we're trying to figure out, how far the plane should be away from the island, or how far the package would travel horizontally. We know the velocity of the plane this time, 186 meters per second. We don't know the time it takes, so we can't do much in the x direction again right now for this problem, because we're missing those two variables. Okay, we're missing both of them, and this would be our equation we're going to use, but I don't know x and I don't know time, so it's not enough information. Let's go to the y direction. We know it's going to fall a distance or displacement of negative 500 meters, because the plane is flying at an altitude of 500 meters. We always know the acceleration in the y direction is negative 9.81 meters per second squared. Again, we know VIY is still 0. It's always going to be 0 when the object is launched horizontally. Always. Okay, tomorrow when we do problems with this, you're going to see that it's always 0 when it's launched horizontally. And we'll figure out the time in the y direction. It's the same exact problem in the y direction. It's identical, just different numbers. So we're going to use the same exact formula. Now, again, VIY is 0. I can cancel that part. And if I solve this for time, it's the same solution. That's why I have you guys solve generically so you can see this. Time is the same thing. Radical 2y over a. It's the exact same expression that we had for the Tom Cruise problem for time. It's not changing at all. So we take 2 times negative 500 meters over the negative 9.81 and take the square root of that answer to figure out the time it takes this object to land from a height of 500 meters when it's dropped. So, the thing I want you to recall is what we derived in that lesson on trig. And if you remember, we did all that work with those triangles, and there was a major conclusion we made at the end, and we boxed it in. That was this right here. Okay, that was the major conclusion that you're seeing. So this should be familiar to you in some way. You should recall this information at least, maybe not memorize it yet. But you will need to remember this, and you will know it. I guarantee you, after doing a few problems, you'll memorize this. Just like as you practice more and more of the quadratic formula, it's easier to memorize something like that. So VIY and VIX, again, simply mean the velocity in the vertical for VIY, velocity in the horizontal for VIX. So as a demo before we get to the next example, let's take a look at a simple example where an object is launched. Give me an angle less than 45. 44. Significantly less than 45. 24. All right, I'll go back to Mike because he was the first to give a suggestion. 24. Sorry, I should have specified. If it's close, it wouldn't be obvious. All right, so 24-degree angle. An object is launched with a velocity of, let's say, 8 meters per second. All right? Now, Josh, you play soccer, right? Oh, you do? Awesome, Josh. Nice. So, when you kick a ball, Josh, if you kick at a low angle, what will most likely happen? Will the ball travel high or far out? If I kick at a low angle, right, like a low angle of 24, which is not drawn to scale, it's a little low. Will the ball travel more outward or more upward? More outward, right, which is common sense as a soccer player. Now, if I'm a baseball player and I'm warming up my catcher, I might throw a ball straight up to get the catcher to warm up practicing catching fly balls that are fouled up. Now, if I launch it at, like, say, an angle of 75 degrees, that's more vertical than it is horizontal, so it'll have a higher vertical velocity, not much of a horizontal velocity. So for this problem, when we come up with VIX and VIY in a moment, you should expect what to happen. What should you expect between those numbers? Which of the two should be larger, VIX or VIY? How come? Exactly, Paul. It's a lower angle, so it's more horizontal motion. Now, what's the midpoint, or the average, or what would be the angle that would probably they'd be the same for, that you could suspect? 45. Okay, that's why when I said to Mike in the beginning, I said, pick an angle much less than 45 for that reason. And think about it. 90 degrees. Ready? Here's 90. This is 90 right here. From the horizontal, here's the horizontal. This is 90. If I launch something at 90 degrees, I'm just launching it straight up. If I launch something at 0 degrees, I'm launching it only horizontal like we did in the last class. If I launch anything between 0 and 90, it's at an angle. 45 is the middle, or the midpoint. If I'm looking, I use midpoint for segments. For angles, it's like the angle bisector would be at 45 degrees. So if you launch something at 45 degrees, it's traditionally, or you're going to see that it's pretty much the same vertically and horizontally. With air resistance, things change, but we're assuming no air resistance. So here, as Paul mentioned, the angle 24 degrees is far less than 45. So we should see more of a VIX than a VIY. All right? So let's go ahead and figure those out. So this is what VIX really is. Okay? VIX is like a vector along the x direction. VIY is like this vector along the y direction. Now, I'm not going to do this, but take a look. If you took this blue line, you have to see this up here. If you took this blue line and moved it over here, wouldn't you get back to that right triangle we've been working with for a while? So take the blue line and superimpose it over here. You would get a blue vertical line right here, and you would end up getting that right triangle we had been working with. That's the reason we're seeing this again with trig. Okay, so let's determine what the velocity in the x is and what the velocity in the y is by using the formula up above. So VIY, I substitute in. The VI is 8 times the sine of the angle, and that should give me some quantity. And then VIX is pretty much the same thing, except instead of sine, I use cos or cosine. Very good. Please, I know you guys are resetting your calculator in math class, and you're probably clearing your memory at times. It's going to go back to radian mode. Remember I talked about this mode thing? So go ahead and check on your calculator right now, but make sure your mode is in degree mode. If it's in radian mode, you're not going to get the right answer. So I'm telling you now to check these, but make sure your mode is on degree mode. If you recently cleared your RAM or reset it or whatever it was that you might have done, it may be in radian mode. How do you check? You hit the button that says mode on the top left, and then you scroll down and look to see if radian or degree is highlighted. You want degree to be highlighted, so go to it and hit enter. Go down and go to the right, highlight degree and hit enter. So what do we get for VIY when you type in 8, Josh, times the sine of 24? 3.25. All right? And I saw Marianne. Marianne, can you give me the VIX? That's okay. No, take your time. I saw you for the last one, so I knew you had it. 7.3. All right, now, let's discuss and make sense of our answers. I call this a sanity check when you're on your test. Does the answer actually make sense? Because I did get answers on your last test that I wanted to be like, oh, that doesn't even seem reasonable. Look at the actual number. You need to make sense of these numbers. Okay? Look, you started with 8 meters per second as the overall velocity. The components of them are always less because it's like the legs of a right triangle. If you made this into a right triangle here, right? Finish off the right triangle. The hypotenuse is 8. We're really finding the adjacent and the opposite legs. They got to be smaller than 8. So if you get any answers bigger than what you started with, it doesn't make sense to start this problem. Clearly we're good. We got 7.3 and we got 3.25. So we're okay so far. Now, what did Paul mention to us earlier about this? That I can tell that the answer is, in the right range. I know that these are generally right when I look at them relative to one another. Relative to one another.
Well, since it's a lower angle, VIX should be bigger than VIY.
Exactly, Jen. That's right. Again, remember, low angles less than 45, the VIX is going to be bigger than VIY because you're mainly kicking like a low line drive. So VIX is clearly bigger than VIY because our angle was 24 degrees. Does that make sense? Okay, the X has to be bigger here. When would the Y be bigger again? When would VIY be bigger than VIX if the angle were, fill in the blank? Good, here, bigger than 45 degrees. If the angle were bigger than 45 degrees. All right? So let's go into this first problem now with this knowledge down pat. All right? It really helps for this first problem. So the next problem, whatever number it is, another Tom Cruise striking again in a new action movie. And he's got to leap between buildings. So, as always, he's running and jumping and doing all this crazy stuff. So we're told that he jumped from the top of one building to the top of another building. The second building is 4 meters away, and it's 2.5 meters lower than the other building, the ceiling of it at least. Okay? After getting a running start, instead of running off the bridge like he did in that other example horizontally, now he's jumping, kind of like boosting himself off at a low angle of only 15 degrees, which makes sense. You can't jump at a really higher angle than that if you're running outward. So he jumps with a velocity of 5 meters per second in general. That's not VIX, not VIY, it's just overall velocity. And the question is, will he make it to the other rooftop? Or will he fall to his miserable death in between these two buildings? Okay, so what might I do to start a problem like this? What might be useful to do? Before I begin anything else? Yeah, good, Kev. Draw it out. All right, let's draw it out. So let's draw the bigger building here. And let's draw the lower building here. Put our ground level here. We'll put maybe some spikes down here in case he doesn't make it. Get some goriness. All right, so I know that this horizontal gap is how much? Horizontal gap is how much? 4 meters. Again, It says the second building is 4 meters away from the first and 2.5 meters below. So I know the 4 meters has to be this direction because I was told that the 2.5 was below. So if I put a dashed line here, I know that this gap is 2.5 meters. Okay, that's what I know so far based on what I've underlined. I can then draw maybe a sample of a projectile moving, a dot or a point in space. So here's Tom Cruise right here. Okay, he jumps at an angle of 15 degrees. If you're drawing a diagram, try and make it reasonable, right? 15 degrees should be a low angle. So if you draw a big angle, it doesn't really make much sense. So let's draw a low angle like this, and let's draw a horizontal line like that. Okay, that angle in there, which is really tough to see, you could like zoom in a lot. Whoops, that's not the zoom in function. Hold on. Okay, if I zoom in a whole lot, I could probably squeeze that angle in there, but that's the angle we're looking at right in there, okay? So this is your theta. This is 15 degrees. Okay, it's probably difficult to see when I zoom out. Oh, you can still kind of see it. All right. So at this point in time, we've labeled our diagram with 15 degrees there, which is almost invisible now. Label it on yours, please. And with an initial velocity of 5 meters per second. Now, it's a stunt movie, it's a sci-fi movie, whatever. Is 5 meters per second actually a reasonable velocity? Think about it. What's a meter? Approximately what? 3 Yeah, it's a little more than 3 feet. It's like yard is 3 feet. So a meter is a little different than a yard. A yard is about 90 centimeters, whereas a meter is 100 centimeters. So we're talking a little more than 3 feet for every meter. So he's running 15 feet every second. So he's got to have some sort of superpowers or something to do that, obviously, right? Okay, so realistically, a real velocity of somebody running, like if I'm running, I might get like, if I run 2 strides every second and my strides are, say, 3 feet long, then I'm only moving 6 feet a second. That's like 2 meters per second. So 2 meters per second is more realistic. We're trying to make Tom Cruise seem like a crazy guy here so he might not die or something. So 5 meters per second is his initial velocity. Okay, but just to make sense of the number, of what it physically means. All right. Question is, will he make it to the rooftop? Will he make it there? Now, this could be a very complicated problem because you're given a lot of information. You're almost given too much information, or you're given enough information to make it confusing. How might you approach this problem? How might you approach it? And we're gonna definitely break it into X and Y like we've done in the other problems. But it says, will he make it to the other rooftop? Will he make it? What might be an approach to start with?
Well, define in the problem, define the amount of distance you cover.
Yeah, remember that problem? That's exactly right, Paul. Very good. Remember the problem you did in your problem set with the girl that throws the apple up, and it was like, will her friend catch it or not? Remember her friend was at like a higher elevation, like 6.5 meters or something? We found the vertical component, or the vertical displacement, and then said, well, was that 6.5 meters? If it was, she did get it. If it wasn't, she didn't. So why don't we do that again here? We know he's going to travel 4 meters at some point in time, right? Because the horizontal velocity is constant. He's going to jump like this, right? Either he's going to jump, and he's going to take one of 3 paths. Ready? He's going to jump, and he's going to make it. He's going to jump, and he's going to just hit the corner, maybe make it, maybe not. Or he's going to jump and smash into this wall and then fall into his death. So at the end of the day, he's definitely going to make the 4 meters, but it's where he is vertically after 4 meters that's important. If he's only, say his vertical displacement is only 1.5 meters down after 4 meters, that means that 1.5 meters, that's like right here. So his path would be something like this. But if after 4 meters horizontally, we determine his y value to be -5 meters, well, -5 meters, this is -2.5 meters from here to here. -5 would be like down here. That means that he would hit the wall all the way down here. He would go too far down, and he would not make it. So let's assume we know x and figure out y. And check it to see if it's less than or greater than that 2.5 meters negatively. Okay? So let's go ahead and make our xy chart like we've done in the past. In the x direction, again, we know the displacement. What is it again? In the x, 4 meters. Okay, 4 meters horizontally. He's definitely traveling at least 4 meters, so we know that's going to happen. We don't know what the y direction is yet. That's what we're trying to figure out. Okay, remember, if this y, the answer for y is more than negative 2.5 meters, he's going to fall to his death. If it's something less than that, in absolute value, I should say, meaning if it's like negative 1.5, that's less than that, or closer to 0 on the number line, he'll just make it. So let's figure out what the y displacement is. What else do we know? What else do we know?
The acceleration.
Accelerations, go.
For y, it's -9.81, and then for x is 0.
Yeah, that is it, but it is. You know it. Okay, no horizontal acceleration ever. Okay, we're never assuming air resistance is involved, so we can always say that's 0. Now, I see this VI at the top of the screen, but I really don't know what to do with it. Somebody tell me, what should I do with this VI now? Because it's not horizontal, but it's not vertical. Again, VI is neither horizontal nor vertical. What should I do? Think about the last slide that we may have just filled in. Something similar to that. Look at your last slide if you need to. Everybody can do this. Scroll back up. What did we do when we were given the V? We broke it into its what? What do we call that? Components, yeah. So Mark says, so yeah, pop up. What would I do here? Exactly. Very good. So what was the formula for VIX, Marcelino?
VIX equals V times cos theta.
All right, so here's what I write. 5 times cos 15. Where's the 5 coming from? That's V. That's the initial velocity at the top. That's the velocity with which Tom Cruise jumped at an angle. So we have his x velocity right there. And what's the difference in the y velocity?
Then you use sin.
Good. Okay, sine of 15 instead of cosine of 15. Now, please go ahead and calculate this number now. You don't have to use the expressions the way they are. You could find the integer or the decimal value rather now. I don't mind that. So just put it on the next line if you want. What do you get when you do 5 cos 15? 4.82? 83. And let's keep 2 decimal spots, at least when we're doing calculations. At the end, we can round. Okay, at the end, we can round. And VIY, somebody else? VIY. What do we got? Steph?
1.29.
1.29. Jen, remind us again why these answers make sense? You told us a moment ago? Because it's, yeah, both of these got to be smaller than the 5 to start. And which one is bigger? Yeah, because it's a low angle. Remember, there's a low angle. The angle is less than 45 degrees. So Vx has to be bigger than Vy. And if they're both definitely less than 5, which was the hypotenuse, right, of the triangle. So if you want to, just put one line through here. So you remember that you've evaluated already. Because I've seen people do this and then go ahead and use this later on and make mistakes. So once you get the number, just put a line through it. But please don't erase it. I want to see the work. I want to see that you wrote this out and that you actually calculated those two. But once you calculate that, just put a line through it. That's fine. All right? Now, what is the only variable I haven't really listed so far? A variable that we tend to use a lot that might connect my two directions. It is time. It is. And what did I call that? I called it the blank variable. Anybody remember from last class? I used a specific word to represent that it can be in both x and y direction. Yeah, the linking variable. Okay, the reason I use the word linking again is because it links the equations that we're going to come up with in two different directions. Remember, time is independent of space. Time is time. It's different. It doesn't matter if you're moving horizontally or vertically. Time it takes to do something is just a matter of duration, not a matter of location. It doesn't matter what path you travel. Time is time. So, if I want to figure out the value for y, right? This is my goal to figure this out. I need some more information here, but I can do something over here. What is the only formula you will always use in the x direction? It is the only formula you're going to use every time. Whenever there's no acceleration.
V equals x over d.
That's it. Now remember, this is really like VIX. Okay, just to specify so we know which one we're using. We're not using a 5 here. We're using a 4.83. It's in the x direction. But that is right. Good, Jake. V equals x over t. I've got x. I've got VIX. So what could I solve for? time. All right, t. How do I solve for time algebraically? How do I rearrange this formula to solve for time algebraically, Marianne?
Well, you can just flip VIX and T.
Yeah, remember, please, folks, whenever you have something that's triangular or a numerator and then a fraction, just flip them. All right, that's the time it takes. Well, we've got those numbers. 4 over 4.83. What does that give me? I know it's a decimal because the numerator is smaller than the denominator. 0.83. That's complete coincidence in the 83 part, right? Please don't let that fool you. 4.83 and 0.83 had nothing to do with those numbers. It's just complete coincidence that you get 83 for both of those. So after not even a second, ready? After not even a second, and I'll scroll back up so you can see this, Tom Cruise has made it across the 4 meters, but the question is, where is he? Is he up here? Is he here? Is he here? Or is he here on his way down to his death? Okay, is he making it or is he not making it? He's definitely made it 4 meters across, so he's somewhere along this line. Because we know it's been 4 meters of duration in the x, or location in the x, and it's been almost a second of duration in time. So the question becomes, let's figure out the y to see where he is now. All right, so that's my linking variable. So what should I do with it if it's the linking variable? If it's in the x direction, I should do what with it? Use it for the y. So let's list that. Okay, remember, whatever you get for time in one direction is the same thing you get in the other direction. So always use that, please. Whenever you're stuck on something, find the time it takes in one direction, and then maybe that will help in the other. Now, looking at this right-hand column here for the y direction, I'm trying to determine y. I've only got 2 equations that give me y. I've got one that says VF equals VI plus AT, but there's no y in there, so that's pointless. Then I've got VF squared equals VI squared plus 2AY. But I don't know anything about VF. There's nothing about final velocity here. Please remember, the final velocity is not 0. Some of you still make that mistake. Just because I'm hitting the ground doesn't mean my final velocity is 0. Final velocity is the velocity the instant before impact. We know nothing about that here. But we do know a lot about time, VI, and A. What formula should I use in the y direction that involves all these, that gives me the y value, the displacement? Which formula is that? Bless you.
VIYT plus 1/2 AT. Oh, sorry, y equals VIYT
Yep.
plus 1/2 AT squared.
Very good. Okay, and remember, these little y's, what are they? They're not variables, they're... What's the word for chemistry? Subscripts, yeah, good, subscripts. Please remember that, folks. This is not a variable. This is not a variable. These are subscripts referring to these 2 things here. Now, somebody in the other class asked, do I need to use the subscripts? If you don't want to, it's fine, as long as you use this column approach like I'm showing you here. So if you didn't write AY, and you didn't write VIY, just wrote VI and A, as long as I know you're working in this direction, I'll read it. But just to specify, it just makes it more obvious, right? At this point, you know VIY, you know time, and you know acceleration. So it's a plug and chug. Plug it in, go right through. Okay, so y equals 1.29 times 0.83 plus 1/2 times negative 9.81 times 0.83 squared. Now you can get a negative or a positive answer here, so don't be discouraged if your answer doesn't seem what you expected it to be right away. And we'll discuss what it means whether negative or positive in this problem. Again, make sure you're checking this, please. I can't emphasize enough how many people made mistakes calculating stuff at the end on their test. All the right work and the calculation was wrong. Even in the last class with the other students, some of them were getting the wrong answer and not checking it right because somebody put like a plus sign right here, when this is clearly a time sign right here between the 9.81 and the 0.83 squared. Okay, so just look for that stuff as you're going through it, please. Look for those simple mistakes or careless mistakes or whatever you call them. Anybody? What do we got? And feel free to do this all in one line, by the way. You can do this all in one line, because PEMDAS will be followed. It's not a problem for this kind of a problem. Paul, what do you got?
Oh wait,
No, not
I
yet?
didn't do it.
Okay. Somebody else? Marianne? Negative 2.2.10? I think it was negative 2.3. Just check real quick, Marianne. Check your work, because I think it was negative 2.3. It's close, so it might have just been some... Negative 2.3. Okay. So what does this mean? Let's go back to the... Did you find the mistake?
Yeah.
All right. Let's go back to the diagram. Negative 2.3 meters. The top building is like the starting point. The next building is 2.5 meters below it. Did he go down more than 2.5 meters? How far did he go down? 2.3 meters. Which means that in reality, this, whoops, let me draw it with this. This is where he ends up after 4 meters. Only 2.3 meters down, or something less than 2.5 meters down. Had you gotten an answer of negative 4 meters, it means that Tom Cruise would have hit the wall down here maybe. Or negative 5 meters, he would have been down here. But it would have been beyond the 2.5 meters that he is allowable to move. Since he only traveled 2.3 meters down, he would have just made it onto that roof, clearing that gap vertically by 0.2 meters. Again, 2.5 is the gap he has vertically. He only went 2.3, so there's still a little bit of space right here. There's 0.2 meters left over right here. He traveled up, he came back to where he started horizontally, or along the horizontal. Then he kept going down, down, and down, which I guess this one right here, down further until he got to negative 2.3 meters. And when he was at negative 2.3 meters, he was right in line with this cliff. All right? Now, it was a long problem, I know. We spent a while talking about this, but we just spent about 20 minutes, well, 18 minutes on that problem alone. I'm going to pause here, okay, because we're going to finish up the last two problems tomorrow in class.